All right, in this lesson, we're going to go through section 4.3, looking all at the ionization of water. So we've probably observed before that water is an amphiprotic ion. It can lose protons or it can lose those hydrogen ions. It can accept hydrogen ions. Water is very special. We do most of our reactions in water. So we're going to look specifically at water today. So some of the goals for this lesson are we're going to describe the auto-ionization in relation to water, so what auto-ionization is. And if you've seen things like autotrophs or automatic, these are things that they do to themselves. We're going to explain how to calculate the concentration of hydronium or hydroxide ions in pure water. We're going to describe how adding an acid or a base to water shifts the equilibrium between my hydronium and a hydroxide. And then finally, we're going to calculate the concentration of hydronium and hydroxide ions when a strong acid is mixed with a strong base. So there's our objectives today. And you'll notice the first type of calculation that we have. So first here, I've got a picture of auto-ionization of water and what's actually happening. We've looked at water in the previous unit and have said that water has some kind of interesting properties. Because water is a polar molecule, this side of the water molecule kind of takes on a partially negative charge. There's my delta negative charge. And the hydrogen side takes on a delta positive side. So we've got those hydrogen bonds that can form between a water molecule, between one and another one. And in rare cases, what happens is there's enough of a hydrogen bond, enough attraction to actually rip one of those hydrogens away and ionize both those molecules. So you'll see here that we actually create a hydronium molecule, hydronium ion, and a hydroxide ion just from having two water molecules come into contact with one another. So that's the auto-ionization of water. So with water, we can have this kind of equilibrium reaction taking place. You'll notice that in the picture represented there, we had two water molecules and they're liquids, and they form a hydronium ion, and that's aqueous because it's dissolved in water, and a hydroxide ion. So there's the equilibrium reaction that's taking place. We can describe that equilibrium by looking at the Kw, the water ionization constant. So again, this is just a special form of an equilibrium reaction. So in this case, Kw, the water ionization constant, is equal to the concentration of hydronium multiplied by the concentration of hydroxide. And you'll notice that we leave out the water altogether because now we've got two water molecules, but they're both in liquid form on the left-hand side. So we leave those out of the expression. As it turns out, at 25 degrees Celsius, which is what we do all of our reactions at, the Kw is equal to 1.0 times 10 to the negative 14. And I want you to pay special attention to this 14 up there because we're going to start talking about pH scale in the next week. And that number there is going to really play into our pH scale. So if you think about our pH scale going from 0 to 14, there's where the 14 comes in. So from this information, we can calculate the concentration of hydronium and hydroxide ions in water at 25 degrees Celsius. So we're going to start here by substituting in everything we know. We know Kw is equal to the concentration of hydronium times the concentration of hydroxide. Now I just told you that at 25 degrees Celsius, Kw is equal to 1.0 times 10 to the negative 14. And what you probably know, but maybe weren't thinking about, is that in pure water, we've got a balance between hydronium and hydroxide. So in pure water, because we've got this ionization taking place, if you're going to create a hydronium ion, you're going to make a hydroxide ion. They're going to exist in a 1-to-1 ratio. So that means we could substitute in H3O plus for both of these. So now instead of two unknowns, I just have one unknown. If I square root, I can find that my concentration of hydronium is equal to 1.0 times 10 to the negative 7 moles per liter. And because we've got a 1-to-1 ratio here, and they're equal, that also means that my concentration of hydroxide is 1.0 times 10 to the negative 7 moles per liter. Now remember how I said pay special attention to this exponent? What do you know is a neutral water on the pH scale? It's a 7. So when we have a concentration of hydronium ions as 1 times 10 to the negative 7, that's where we get neutral water. That's where we get our pH of 7. Now when we add an acid or a base to that water, it causes equilibrium to shift. So if we look at that equilibrium between my water molecule and the ions, H3O plus, if I add an acid or a base, it causes equilibrium to shift. So let's just say, for example, if we added an acid, we're going to be increasing the concentration of hydronium ions. That's going to shift equilibrium to the left-hand side, and it's actually going to decrease the concentration of OH minus. So there's the first one that we can kind of look at. With a base, if we increase the concentration of base, we're increasing the number of hydroxide ions. Again, we're shifting equilibrium to the left here, but we're going to be decreasing the number of hydronium ions. So there's this little balance and power play that takes place between these two ions. And both hydronium and hydroxide ions are going to exist in all aqueous solutions. What we care about is if we've got more hydroxide ions, that means the solution is acidic. If they're equal, we've got a neutral solution. And if my hydronium are less than the hydroxide, that solution is going to be basic. So our last objective here today is looking at mixing solutions of strong acids and bases. We're going to be looking at what happens when we neutralize things. Because if we add an acid to a base, we can make water. And if we make our water, we're neutralizing, and we can mix strong acids and bases, and they dilute and neutralize. So when strong acids and bases are mixed, the following things are going to happen. The solutions will dilute one another, so we're going to be using a dilution formula. Hydronium and hydroxide are going to react together to neutralize, and the resulting mixture will be acidic or basic or neutral. So if we take a look at what's happening here, it says, what is the final concentration of hydronium when 25 milliliters of hydrochloric acid, 0.3 molar, is added to 35 milliliters of 0.5 molar sodium hydroxide? So here I've got a strong acid, I've got a strong base. So I'm going to have that neutralization taking place. When I have HCl mixed with NaOH, we form water, H2O, plus a salt, NaCl. So there's where the neutralization takes place. And kind of what's happening is the hydroxide is mixing with the hydronium ions to form water molecules. So that's really what's happening at a molecular level. So what we're going to do is look at how those solutions dilute one another. So I'm going to look at it from two perspectives. First, the hydrochloric acid. So I'm going to use my dilution formula, C1V1 equals C2V2. The original concentration of hydrochloric acid is 0.3. Original volume is 25 milliliters. And you can change that to liters if you'd like. It doesn't matter with this particular equation, as long as you keep it consistent throughout. So my final concentration is really the concentration of hydrochloric acid at the end, which is going to be equal to 0.3 times 25. We're going to rearrange this formula, and my final concentration of HCl is equal to 1.25 times 10 to the negative 1 moles per liter. So there's looking at it from the first perspective. Sorry, my screen went blank there for a minute. I hope you're still able to watch. Okay, second one here is what happens from the sodium hydroxide's perspective. So again, we're going to do that C1V1 equals C2V2. Original concentration of the sodium hydroxide is 0.5, 35 milliliters of it. C2 is what we're trying to find. And I've got the 35 milliliters plus the 25 milliliters because we're diluting again. So my final concentration, that C2 of NaOH, is going to be equal to 2.92 times 10 to the negative 1 moles per liter. Okay, going through the exact same situation for the math. Now what I want you to take a look at is which do we have more of? Is this going to be a basic solution or is this going to be an acidic solution after the neutralization takes place? So if we can compare these two numbers, you'll notice that we have a higher concentration of NaOH. So I have base in excess. So my final solution is actually going to be basic. Now we want to figure out how much excess we have. So how much excess, the concentration of my hydroxide ions that I have in excess, we're just going to do a subtraction. So I'm canceling these out because everything's going to neutralize. So I get a final concentration of sodium hydroxide, or just hydroxide if we look at how it dissociates, of 0.167 moles per liter. Now, even though I've gone through all those steps, we still haven't answered the question. It asks what the final concentration of hydronium is going to be when 25 milliliters reacts. So I'm just going to change my ink here for a second. To figure out what the hydronium is going to be, we're going to go back to this Kw expression. And Kw is equal to the concentration of hydronium, this is what we're trying to find, times the concentration of hydroxide. So I've got 1.0 times 10 to the negative 14. We're going to assume 25 degrees Celsius, if we're not told otherwise. I'm going to try and solve for the concentration of hydronium, and I'm going to substitute that excess hydroxide into the expression. So I'm going to rearrange this formula, solve for the concentration of hydronium, and I get 5.99, I guess we're going to go 6.0 times 10 to the negative 14 moles per liter. So there we go, 6.0 times 10 to the negative 14 moles per liter is the answer to that question. So mixing solutions of strong acids and bases, we're really building on some of the foundations that we learned about with the dilution in the last unit. We're looking at building on some of the concepts that you learned in grade 11 with looking at what's in excess. And then we're bringing in that Kw expression. So this is usually a topic that most Chemistry 12 students struggle with a little bit. So make sure you do a couple of practice questions. There's some practice questions in your textbook as well that I'd like you to try. And good luck with it. Let me know if you have